Okay, we'll get started here. Let's all right. Oh no, I do want to check in and see how you guys are doing. I don't know. How are we doing? Okay. Okay. Well, I'm happy to see you guys here. I'm always saddened by tragic events, and but I'm happy to see you guys. So this weekend we observe Veterans Day, and so there's no class on Monday, and so we'll see you guys on Wednesday, and on Wednesday we'll have a midterm exam. So I just want to talk about that. Okay. So this will be midterm 2, and I'll kind of go over the contents of the exam, and just so you guys can adequately and appropriately prepare. So okay, so there's definitely going to be a question on basically a Bayesian inference question. Okay, and you will have it. There will be I will provide data, and this will use a conjugate prior. Okay, so conjugate prior, and you will find you are responsible finding the posterior distribution after seeing some data. Okay, so I will not tell you exactly what it will look like. Okay, so some examples we've seen was the data comes from a binomial, and the prior is a beta distribution. Okay. Okay, so that's been in the lectures. In the homework, you have the data coming from exponential, and the prior is a gamma distribution. Okay, and you can go on Wikipedia and you can look up conjugate prior. And there will be a table of conjugate priors, kind of listing off, so here, if the data, the likelihood is binomial, then the conjugate prior is a beta, okay? And if the, likelihood is Poisson, then the conjugate prior is gamma. If the likelihood is multinomial, the conjugate prior is Dirichlet. And, if the likelihood is normal, the conjugate prior is also normal, at least for the mean. And, for the variance, you got squared inverse gamma and things like that. And so you can kind of look through these and just get an estimate. And I imagine you can make up your own problem here. And so this will be, a little bit more mathy based. I would say look at the problem in homework 4. Problem 1 is probably a good example, and you can try to make up your own questions there. And then I think in Wednesday's class, at the last bit, I kind of covered a lot of the approach for doing homework 4, problem 1, without directly giving you the answer. I think I gave you a lot of hints in Wednesday's lecture. Oh, I have this. Let me move this. Move to 102C. Okay, so yeah, if you look at week 6 Wednesday, I talk about how to go for homework 4, number 1. Okay. All right, so that's going to be your first problem. Another problem you'll have will be maybe a Metropolis algorithm. The discrete case. Okay. And so, I will describe a scenario of, possible states. And then you will have to create, I will also provide a target distribution. All right. And then your job will be to create the, and I'll also provide a proposal distribution, okay? Provide or describe proposal distribution. Okay, and you will create the transition matrix. You will I guess look at if I give you the current distribution, you will find the distribution at the next time interval. And find the stationary distribution. Okay, and then maybe show that the stationary distribution indeed is stationary. Are there questions on this? Does that make sense? What you would have to do there? Okay, try. And then we'll have a Metropolis algorithm. Continuous case. Okay, so I will provide PDF of a target distribution. Okay, and then I will also describe a proposal distribution. I'll go ahead and I'll tell you. The proposal distribution will either be a uniform distribution centered at xk, with bounds xk minus 1 to xk plus 1, or a normal distribution centered at xk with standard deviation equal to 1. Okay, so that will be, I'll give you either one of those for your proposal distribution. And then I will give you an arbitrary starting point. And then you will manually perform, a few iterations of the Metropolis algorithm. Okay. And I guess I'll give you a sequence of random views. Okay, so I don't know how much I want to say. So for the proposal distribution, you will, use inverse CDF to get your proposed values. Okay, so if I, okay, so you should be able to do this easily. For the uniform proposal. And then, and if the proposal is the normal, okay, I will provide a normal CDF table. Is that okay? So I feel like I've given you, I'm telling you a lot here, and you can like write your own problems and try this out, okay? And if you take some time to try to like write out the problem yourself and try to do the thing yourself, I think you will do well, okay? I know the homework is based in R, and this is paper and pencil, but I think this, all it does is it just ensures, or the goal of this exam is to make sure that you understand how these algorithms are working on a step-by-step basis, okay? And I think it's going to be important, when you code, you need to know what's happening step by step. And likewise, I think these questions will we'll make sure that you know what's happening step by step. Okay. All right. Are there questions on this? Either of these cases? All right. So we can go, we can do inverse CDF for these methods, getting our proposed values centered at xk, things like that. Yes, question?
Does the midterm cover up to today's lecture?
The midterm covers what I've written up here. Okay? And there's no surprises, all right? You're gonna get the midterm and it's gonna be this, all right? It's just I didn't give you all the details of the problem, but I've given you a lot, okay? I feel like I'm very fair in that regard here. So yeah, okay. Other questions? Yes?
So only 3 questions on midterm?
Only 3 questions, okay. All right, anything else? All right, this. Okay. All right, well, good luck as you study there. Okay, before we move on in content, I just want to address any questions. Not a whole lot of people have been coming to office hours. I'm very excited whenever someone does come. And I'll tell you, I'm very excited when a student comes to ask questions about material and content from the course, okay? I'm not so thrilled about point battles, okay? Like when someone demands points back on their homework. I feel like the graders, I know sometimes they make mistakes, and I'm happy to correct mistakes that the graders make. It's not my favorite thing to argue about, what constitutes, whether the penalty that the grader described is an appropriate markdown or whatnot, But anyway, on Piazza, I see a lot of questions being asked, and a lot of these are good questions, and I'm happy to try to chime in with some answers that clarify any concepts. I do think, though, that many of you, I want to invite you guys to come to office hours and ask questions. I think I can answer questions a little bit better in person than via typing them out. But anyway, all right. Let's. I want to show you guys what I think is a pretty neat application of the Metropolis algorithm, and I think it's fun. So okay, so here's this is what we're going to do. Okay, we've got application of the Metropolis algorithm. We're not going to get to. We're going to run out of time in today's lecture, and then we're not going to be able to continue this on until 1 week from today, because we've got no class on Monday, we've got a midterm on Wednesday, and then so the next lecture on it will be 1 week. So I hope, even though I started it today, you're not going to forget everything I've said today, and so next Friday when we continue this, we can kind of pick up. Okay. All right. So here's the problem. Okay. The thing that we want to solve. Okay. Is we have ciphered text. Okay, so we want to decipher some ciphered text. Okay, so this is not encrypted text, it's cipher text. Okay, so cipher is basically what, I don't know if you guys ever did this when you were like 10 years old, but maybe you pretended to play spies or send secret messages to your friends, and you would have this decoder key, and you would have like A, the letter A goes to the letter M, and the letter B goes to the letter K, and the letter C corresponds to the letter J. And then you would have to write out, some message like hello, and then you would say, okay, well, H goes to the letter, J, and you would cipher the text this way. Then your friend, who also needs to have a matching decoder key, will then be able to decipher the text that you've sent. Okay, so it's about as simple of a making your message hidden, right? So ciphertext, you've got A goes to, I'm just making some stuff up here. All right, and so if you receive the message, I don't know, KMJ, then you have to decipher, and you'd say, oh, this was BAD, right? So bad gets ciphered into this, and then it gets deciphered back into this way, right? And so this is what we have, all right? Okay, and then so apparently some guards in a prison intercepted these messages that prisoners were passing to each other. And, apparently, they had hidden the decoder key somewhere that the guards couldn't find. But they had these messages, and they wanted to know, what are the prisoners saying to each other? And they figured it was going to be most likely a simple cipher and not like some kind of algorithmic encryption that would require, something quite difficult, right? So we have intercepted some kind of, or intercepted a message that has been ciphered. Okay, and we wish to decipher it, even though we do not have the decoder key. Okay. All right. So does this kind of make sense? What's going on? Did you guys ever do this as a kid? Write secret messages in this way, and then you realized after like trying it out, it was like way too hard and frustrating to do this manually, right? Okay. All right, so this is what we've got. All right, so how are we going to do this? Okay, so I'm going to describe this as kind of as a Bayesian problem. Okay, so there is an unknown decoder key. Okay, and this decoder key is going to be a mapping of the 26 letters to 26 letters, okay? So there's some unknown decoder key, and the decoder key is just a mapping of the letters A through Z to basically a scrambled version of A through Z, right? To 26 letters scrambled. And we just don't know what it is, okay? How many possible mappings are there? Just what do you guys think? Anybody? I feel like somebody should know this answer. 26 factorial. Thank you. There's 26 factorial possible mappings, right? Because the letter A can be mapped to any of the 26 letters, and then B can be mapped to any of the 25 remaining letters, and C can be mapped to any of the 24 remaining letters, all the way down until you get to the end where the last letter has to be mapped to the last remaining letter. Okay, so there's 26 factorial, and what is 26 factorial? It's a big number. 4 times 10 to the 26. That's a coincidence. Okay, so this is about 4.03 times 10 to the 26 possible mappings. All right, so it's like too much work to try to brute force this, okay? There's too many for just a brute force. Okay, but this is the unknown thing. And so what we can do, and what we want to know which of these 26 factorial mappings is the correct one, right? Okay. And effectively is we can say there's actually a distribution, a discrete distribution over all 26 factorial mappings, okay? Okay, and this would be the probability of, we'll say the mapping is theta given our data. This will be a discrete probability distribution. And what we expect is that the correct one will have the highest probability, and the ones that are wrong will have lower probabilities, okay? Have the highest, or at least a very high probability. And wrong ones will have low probabilities. Okay? So for example, we want to say, let's say we have some ciphertext, blah, 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 okay? And then when we decipher it, okay, decipher using, we'll say theta 1, if this translates to how are you, well, no question, no punctuation. How are you? We want to give this sounds like a reasonable thing, right? Versus like another probability, okay? Another possible map, theta 2 could be I don't know, hot are you, all right? Now, this is also quite possible, right? The only difference is that one mapped, you know, like the third letter got mapped to W, and over here the third letter got mapped to T. These are also possibles, right? But then, you know, another possible could be, say, theta 3, and this is, I don't know, X, N, K, P, Q, S, and then W, and then O has to be N again, and then U would be, I don't know, G. All right, and this we would say this has to be, this can't be right? So this one, we would give this one a low probability, and these ones will both have high probabilities. Okay, does that make sense? And so the answer is, you know, we probably won't know, like if this is the message that that we've intercepted, we can't be sure if it's how are you versus hot are you, okay? Because it could just be like somebody wants to check in on how someone's doing versus someone's giving them a weird compliment. And we're not sure, you know, based on our semantic understanding of the English language, we're probably inclined to believe that how are you is more likely, okay? But you know, we can be quite confident that, you know, if we found some decoder key and we used it and it produces this message, we can be pretty sure, like, this is not going to be the right decoder key, right? Like, I don't know, let's say you've come across the prisoner's decoder key room, and, you know, some of them are old ones that they no longer use, and you have other ones, and one of them translates to something that you can kind of understand. You go, oh, well, maybe this is likely, okay? So this is what we're going for. We want to get, you know, what's the probability of a specific decoder key given the encrypted, or not encrypted, the ciphered message that we've intercepted, right? So, you know, this could be, you know, we intercepted A, G, T, blah, 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 right? Okay. So, Bayes' rule says probability of theta given the data is going to equal probability of the data given theta times the probability of theta divided by probability of the data. Okay. And we're going to use Metropolis algorithm. Okay. So we will use Metropolis algorithm. So that means, what can we ignore? We can safely ignore the denominator probability of the data, which is a constant, which is a normalizing constant that, you know, cancels out in p move equals minimum of 1 of probability of theta propose versus probability of theta current. Okay, so we can safely ignore this, all right? So right now we've got probability of theta given data is going to be proportional to the probability of data given theta times the probability of theta. Okay, is that all right? Because the probability of data, this would be a pain to calculate because we have to consider every single possible mapping and find the total probabilities, the total of the numerators across every single possible one. And that involves finding all 4 to the times 10 to the 26, you know, finding all 26 factorial possible mappings and considering every single one of them and saying, what's the probability of getting this ciphered message if I've considered every single possible thing, which is just impossible, not impossible, but it's not easy to do, okay? It's like really practically impossible. Okay, so this is what we have. All right, what is probability of theta? Probability of theta is our prior distribution. On prior distribution on theta, or prior distribution of theta. Okay, theta represents the letter mappings, right? Theta is the secret letter mapping. Okay, what do you think would make sense for a prior distribution for theta? Do we have any inclination to believe that one particular mapping is more likely than another particular mapping? No, okay? So I would say our prior distribution of theta should be a uniform one, saying all 26 factorial, before I look at the data, all 26 factorial mappings are equally likely, okay? So we'll say theta is the secret letter mapping, and we have no reason to believe why one mapping is more likely than another. Okay, but so we use a uniform prior, okay? And this will just mean all 26 factorial mappings are equally likely prior to seeing the data. Right? Is that okay? So that means probability of theta is a constant for all thetas. Okay, so for all of the mappings that we have, every single, all of them have the same prior distribution. Okay, so that further reduces our posterior distribution to just be proportional to the likelihood. Okay. All right, is this okay? All right, so this is the hard part, which is how can we talk about the likelihood of getting an encrypted message given a particular cipher? Okay, how can we measure the likelihood or the probability of a ciphered message given a particular decoder key? Right? And so this is where we just have to come up with we're going to come up with a kind of a simple model to represent what we believe to be, likely versus unlikely values, right? So we will make a simple model to help us figure out what data is likely versus unlikely. And so, when we think of messages that we send to each other, there's complicated rules in how to construct a sentence, right? And you learn this just from listening as a baby, and your brain is primed for acquiring language. And so, whatever language your parents spoke, that's going to be the language you first acquire. And, we learn these things, and, linguistics experts will tell you, blah, 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 and semantics and syntax and all of this stuff, okay? That's probably going to make it too complicated for us to program here, all right? So we're going to program a simple model that will just say, you know what? If the message contains words like the and is and a, those are common words that show up in English. And so if the message produces those, that sounds pretty good, right? Okay. If it produces other common words, we'll say that's more likely, okay? If it produces nonsense words like, what do I have up here? XNK and WNG and PQS, then we'll say this is probably not correct, okay? So one way to model how likely our thing is just keeping it a simple thing, we're just gonna say, are we producing real words versus nonsense gibberish, okay? And we're gonna assign higher probabilities to real words and lower probabilities to nonsense gibberish, okay? And if we have a lexicon or some kind of table of words that says, the most common word in the English language is, I don't know, one of those words, right? And then we'll say, okay, we're going to assign that word the highest probability, and then, words like house is common, but not as common as the, and then words like, I don't know, pepperoni is probably less common than house, okay? And I don't know. Other words, less common words are out there also. But even if it's a real word, it should have some kind of value, and a fake word will have like very low probabilities, right? So we'll make a simple model to help us figure out. Okay, so part of this will be, we will give high probabilities to real words and very low probabilities to nonsense words. Now, why would I give a very low and not a 0 probability? Like, why wouldn't I assign the probability of x and k to be 0?
Possible.
Huh?
It's possible.
It's possible, right? I don't know. The prisoners might be trying to actually send something and say like, do you have the secret XNK? Maybe that's a code word for something, right? So it's not a 0 probability. It's not a word that we would normally use in our daily language, but it's also not a 0 probability. There is a possibility that they wanted to actually communicate that nonsense word. But we're just going to assign a very low probability to it, okay? To kind of enhance this, we enhance this by giving higher probabilities to common words like a, the, is, I don't know, run, stuff like that, okay? And then, lower, but not super low, to less common words. Like, I don't know, aardvark, and I don't know, some other uncommon word, right? Okay. All right, so that's one strategy, okay? And we could implement this. And this part, less lower but not, this will require a resource kind of listing word frequencies. Okay, so we might be able to find some kind of thing that says these are all the words in the English language, and these words are more common and these words are less common. Okay, so that will require some kind of resource, but we might be able to get one. Okay, we can do this, but what happens is we'll often run into a problem in the beginning where we have one bad deciphering text, and or we have one decoder key that is not correct, and then we have another possible decoder key that's also wrong, and both of them just produce all nonsense words. Okay, both of them all produce nonsense words, and in our setup, they will both have the same very low probability score because they're both producing nonsense words, right? So a limitation, all right, is that if you have two wrong decoder keys, they may both produce nonsense. Okay, so you might have X, N, K, S, P, J, and T, V, T, W, R. Okay, so this is we'll say theta 1, but then you might have another one that produces D-O, L, and H-E, K, and A-N-P, okay? And these are both get the same low score for having all nonsense words. However, one of these looks more like English than the other, right? And we would say the second line, even though it's all nonsense words, we would say this one seems a little bit more likely than the top one, right? So we'll talk about we'll resume on next Friday, but we want to be able to say, okay, the second one we should still assign a higher probability than the first one, even though it's producing all nonsense, okay? All right. Okay, we'll end here, and we'll see you guys on Wednesday for the midterm exam. Good luck as you guys study.
Probably.